You know, the world is just full of these hidden rules. They're patterns that connect, say, the speed of your car to when you'll get there, or how many things you put in your shopping cart to your final bill. Today, we're going to pull back the curtain on two of the most common rules out there, direct and inverse variations. Let's dive in. I mean, really think about it for a second. We kind of know this stuff intuitively, right? You know that if you add more stuff to your cart, the bill's going to go up. Or if you drive faster, your travel time's going to go down. These things aren't random at all. They're actually super predictable patterns. Okay, here's a classic example. You're at the store. As you add more articles, more items into your cart, what happens? The total cost goes up. They rise together, perfectly in sync. One goes up, the other goes up. Simple as that. But then there's the flip side. Let's say you're running late. The faster you drive, the less time it takes to get to where you're going. See what happened there? As one thing goes up, your speed, the other thing goes down, your time. They're moving in opposite directions. So these two scenarios, they actually follow some pretty straightforward mathematical rules called variations. And believe me, by the end of our time here, you'll have the tools to not only spot these patterns, but to use them to solve all kinds of real-world problems. So here's our game plan. We'll start by looking at these patterns. Then we'll break down direct and inverse variation. After that, we'll put it all to work and solve some problems, including some of those classic brain teasers about time, work, and people. First up, let's talk about direct variation. Honestly, the easiest way to get this is just to think more is more. When one thing goes up, the other one goes up right along with it. And the textbook definition is pretty clear. An increase in one thing causes a corresponding increase in the other. And of course, the opposite is true too. A decrease in one means a decrease in the other. They're locked together, kind of like two people riding a tandem bike. Now this is the secret code right here. This little formula is all you need. If two things, let's call them x and y, are in direct variation, their ratio is always constant. That means if you take x and divide it by y, you'll always get the same number. We just call that number k. And what's so cool about this slide is that you can see the rule in action. We've got the number of articles and how much they cost. So let's check the math. If we divide the articles by the cost in each column, what's 8 divided by 40? That's 1/5. How about 10 divided by 50? Yep, 1/5 again. 15 by 75. You guessed it, 1/5. The ratio stays the same. That is direct variation right there. Okay, let's switch gears and look at the opposite idea. Inverse variation. If direct variation is that tandem bike, then this is a seesaw. When one side goes up, the other side has to come down. The formal definition here totally backs up our seesaw idea. An increase in one thing causes a decrease in the other. Just think back to that driving example. More speed means less time. And here it is, the second secret code you need for today. For inverse variation, it's not the ratio that's constant, it's the product. This time, if you multiply the two quantities, x and y, together, you will always get the same number, that constant k. This slide just lays it out perfectly. Take a look at the table. As x gets bigger, y gets smaller. But what happens when you multiply them? Okay, 2 times 32 is 64. What about 4 times 16? Also 64. 8 times 8? Still 64. The product? It's always the same. So let's just put it all side by side to make sure it sticks. Direct variation, they move up together. Their ratio is constant. Think tandem bike. Inverse variation, one goes up, the other goes down. Their product is constant. Think seesaw. That's really the whole thing in a nutshell. All right, now for the really fun part. We've got the rules, so let's actually put them to work. This is where understanding these ideas turns into a legit superpower for solving problems. Okay, here's a classic problem. Let's try to figure this out. If you have 78 men and they can finish a job in 140 days, what happens if you only have 42 men? Is it going to take more time or less time? So, what's the very first thing we have to do? We've got to figure out what kind of relationship we're dealing with. Let's just think it through. If you have more people working on a project, is it going to take more time or less time? Well, it's going to take less time for sure. So, as the number of men goes down, the number of days has to go up. That's our seesaw. It's an inverse variation. And since we know it's inverse, we use our inverse rule. The product is always constant. So the number of men times the number of days in the first situation has to equal the number of men times the number of days in the second. That means 78 times 140 has to equal 42 times, well, whatever our unknown number of days is. And when you run the numbers, boom, you find out it's going to take those 42 men 260 days to finish the same job. And that makes total sense, right? Fewer workers means more time. Let's tackle one more. These work rate problems can seem really tricky at first, but they use the exact same logic we've been talking about. So here's the setup. You've got person A, who's pretty fast. They can finish a job all by themselves in 80 days. Then you've got person B, who takes a little longer, 100 days. The big question is, what happens if they team up? How fast can they get it done together? The whole trick to these problems is to stop thinking about the total job and start thinking about their rate of work. Like, how much of the job do they finish in just one day? Well, for worker A, it's 1/80th of the job. For B, it's 1/100th. To get their combined power, we just add those daily rates together. So we add 1/80 plus 1/100. Find a common denominator, which is 400, and that gives us 9/400. So together, they knock out 9/400ths of the job every single day. From there, we can figure out the total time. And that really gets to the heart of it, doesn't it? It's not about memorizing a bunch of formulas. It's about learning to see the relationship underneath it all. Is it a more is more kind of thing, or is it a seesaw? Once you see that, the math is actually the easy part. So I'll leave you with this question. As you go about your day tomorrow, just look around. Look for these patterns. You'll see them in the relationship between the gas you put in your car and how far you can drive, or the number of people sharing a pizza and how big your slice is. These hidden rules are literally everywhere. And now you know exactly how to spot them.